Well, it's great to be here. Thank you to Liam and the organizers for putting this together. It's really great to see a lot of unfamiliar faces in the audience, because that means that there are more people in the world who want to learn Heegaard Floer homology. So this is a huge subject, and there are an awful lot of things that one can cover. Just to give you a sort of overview of what I'm going to do this week. Today I'm going to do some of the just sort of basic background on Heegaard Floer homology. Can I just see by show of hands how many people have seen sort of some background on Heegaard Floer homology? Okay, a lot have. How many have not? Don't be shy. Okay, so today I was going to just sort of go over the basics, because I think it's probably good to all be on the same page. A lot of the work, the things that Cameron and others are going to be talking about are going to be related to the various problems related to L spaces and geometric properties of L spaces. So I think that's some terminology that I want to be able to establish. Tomorrow we will continue in this vein. We'll talk about knot Floer homology and the various surgery formulas that are out there for understanding the Floer homology of surgeries on a knot in terms of some invariance of the knot itself. And then Wednesday, we're going to do bordered Floer homology. At least, we'll get some sort of basic background on that, and both the algebra that one needs, and then the whole structure of that theory, probably focusing primarily on the torus boundary case, in part to keep things simple. And Thursday, we'll continue with that, some sort of more advanced topics in that area. One of the things, assuming there's time, is to look at some papers of Eftekari that have an interesting perspective on the bordered theory that is sort of not as well known to many people. And then on Friday, Liam will take over, and he will talk about the recent work with Hanselman and Rasmussen on this sort of immersed curves description of bordered Floer homology, and all of the really powerful stuff that you can do with that. So that's sort of an overview. In terms of things that one can read if you're interested in sort of some supplemental things, certainly for the first half of the course, the Odervath and Szabo's old introductory notes from the Budapest seminar in 2004 are really fantastic. There are two papers. One is called Introduction to Heegaard Floer homology, and then one is called Lectures on Heegaard Floer homology. And I was looking them over again, and they're really good, and there are a lot of good exercises in there. So there will be things that I suggest to do as exercises, but those, certainly for graduate students, are actually a great way into the field. Obviously, that it doesn't cover a lot of the more recent work, so when we get to bordered, I will have some more suggestions. Robert Lipschitz has some nice notes on the bordered field from Budapest a few some years later. So anyway, so that's those are some good references, and I would say let's just jump in. So as I said, right now what I just want to do is go over the construction of the original Heegaard Floer construction and talk about the complex. Oh, the other thing I should say is my goal is to not spend too much time getting deep into the weeds of holomorphic curves. One could do that. One could spend an entire semester going into the weeds of holomorphic curves. I think my goal is to take more of a big picture here and understand the big picture of the story, but we'll certainly say a little bit about that. Okay, any questions before I start? If so, I'm probably in trouble. Okay, so what is Heegaard Floer homology? Well, as people probably know, so the idea okay, so throughout So y is usually going to represent a closed, oriented three-manifold. Okay? And what we're going to try to do is assign to y some groups, abelian groups, hf hat of y, that's sort of going to be the most basic version, and then hf plus of y, hf minus of y, and hf infinity of y. Those are going to be the basic invariants. This is going to be a finitely generated abelian group. These three are all going to be modules over the ring Z adjoin U. I guess this is also a module over Z adjoin U, but U is 0. And those are going to be the our basic objects of study. Now, each one of these is going to decompose. So often, sometimes people write just HF circle to mean any of these versions, or I might just write HF, is going to decompose as a direct sum of terms. And the terms, the summands are going to correspond to spin C structures. Okay, so spin C structures can be thought of as certain kinds of bundles over your three-manifold. We don't really need to say much about what a spin C structure is, other than to say that they are in bijective correspondence with H upper 2 of the three-manifold. And this is as sort of affine correspondence, and that is to say that I can, if I start with one spin C structure, then by adding elements of H upper 2, I get all the rest. Okay, but there's not a canonical choice of 0, except in certain circumstances. Okay, so there's going to be this kind of decomposition, and we're going to see where that comes from soon. Okay, and then just now, what about the four-dimensional side of this story? So given a smooth four-dimensional compact cobordism W from y1 to y2, so that is to say the boundary of W is equal to minus y1 disjoint union y2, we're supposed to get maps on this theory. Okay, this is a topological quantum field theory. We want maps. And now, if we want to really do this correctly, what we're going to use the spin C structure on the four-manifold as well. What we end up getting is a map from F circ W from W comma S from the Floer homology of y1 in that summand to the Floer homology of y2. Maybe I'll just call that S2. So S1 and S2 are supposed to mean the restrictions of the spin C structure to that three-manifold. Okay, and we get these maps, and all of these are going to form this. So this is the sort of overall overarching structure of the theory, and we can do a huge amount of stuff with all of these things. And maybe I won't focus so much on the applications in this lecture, just because I could spend a whole week talking about things that one could do with this. So, but this is just going to be, sort of a little overview of what our basic objects of study are, and you'll hear more about all of the amazing things that one can do with these. These really tend to be very good for a wide variety of 3+1 dimensional applications, right? So you have some, generally we're going to, whenever we're talking about problems where we're interested in three manifolds as they occur as the boundaries of four manifolds, this is going to be an amazing set of tools. It also has some more like explicitly three-dimensional applications and explicitly four-dimensional applications, but the interface tends to be the place where all of this, where everything happens. So, okay, why don't we start talking about where these tools come from. Okay, so let's begin at the beginning with the Heegaard side of the story. Heegaard Floer homology, developed neither by Heegaard nor by Floer, but by Ojvath and Szabo. So let's start with a Heegaard diagram. Okay, so I'm going to steal a line from Josh Green here. So what is a Heegaard diagram? Well, it's going to be, so a surface S, so this is going to be a surface, and a base point Z. And now I'm going to have two sets of curves, alpha and beta, and then everything should be oriented. And conveniently, it spells Szabo. Okay, so what are these things? So actually, I want to call my surface sigma. Okay, so sigma is going to be a closed-oriented surface. Of genus G, let's say. Okay, alpha and beta. So alpha is going to be a G tuple of disjoint simply closed curves in sigma, and these are going to be linearly independent in H1 of sigma. Okay, so I have a surface of genus G. I have G curves on there. Okay, beta is going to be another such collection. Z is going to be a base point in the complement of those curves. Okay, the alpha curves and the beta curves are allowed to intersect. Indeed, they do intersect generally, and they are going to be required to be transverse to each other. Okay, so how does this correspond to a three manifold in some way? So what we're going to do to obtain a three manifold from such a diagram, well, what we're going to do, let's maybe try to draw a picture. General rule is alphas are red, betas are blue. There could be a nice poetic conclusion to that, but I will leave that up to you. So alpha and beta. Okay, so what we're going to do, let's start with sigma cross I. Okay, and then what we'll do is we're going to attach our two handles along the alpha at the bottom and the beta at the top. Okay, so maybe these are my alpha circles and these are my beta circles, and so we'll attach these two handles there. Okay, and then the two handles on the top. Okay, that's really impressionistic artwork there. So now what happens, right? So now if I've taken a surface of genus G and surged out G linearly independent curves, I end up with a sphere. Okay, and then attach three balls. as well, and now I end up with the closed 3 manifold. Okay, now of course any closed 3 manifold can be obtained in this fashion, so to get a Heegaard diagram, well, what we're going to do is take a self-indexing Morse function. So take a self-indexing Morse function f from y to the interval from 0 to 3, which is going to have one index 0 critical points, g index 1s, g index 2, and 1 index 3. Okay, and then we're going to take sigma to be f inverse of 3/2. Okay, which is going to be the level set in between the index 1 and the index 2 critical points, and then the alpha and the beta circles are going to come from the so I guess then what we want to do is look at the ascending and descending sets of the critical points. So the alpha will be the intersections of sigma with the ascending manifolds of index 1 critical points, and then the betas similarly will be the descending of index 2s. Okay, and oh, is that a question? No. Okay, and then the base point is going to specify a single flow line that goes from the alpha, from the index 0 to the index 3, right? Because it doesn't, the fact that it is not on the, that it's not on any of the alpha or beta curves tells you that if you flow from it, it doesn't get stuck on an index 1 or an index 2, so it goes all the way to the top and all the way to the bottom. Okay, so that's what where these things come from topologically. Maybe I should draw a picture of one of these. Here's your nice most basic example. Sort of the simplest thing we can do. Actually, I guess the simplest thing I could do would be to draw a genus 0 Heegaard diagram, a sphere, and draw 0 alpha circles and 0 beta circles. And that will specify for me a gluing of 2 3 balls, which is going to produce the 3 sphere. One step up in complexity is this, which again, so now I'm specifying 2 solid tori, and you can picture this, if you like, as being, again, the 3 sphere, where the inner handle body, the inner solid torus, as drawn on the blackboard, represents there's a disk being bounded by this blue curve, and the red curve bounds a disk on the outside, on the exterior, and so this again is going to specify that's 3. Okay, convention that we will always try to follow, and is that we orient sigma as the boundary of the alpha handle body. Okay, which is to say, that is, say, everything that lives underneath the level, the 3/2 level set. It's oriented as the boundary of that. Okay, so that's just going to be our convention. Great. So now, I guess I could draw some more examples of this. So where should we go from here? How are we going to get some kind of data out of this? So let's define, so let's say the alpha curves, let's just index them alpha 1 through alpha g. Okay, so what we're going to be interested in doing is looking at a chain complex which is determined by the intersection patterns of the alphas and the betas. Okay, and so we may as well start saying what our generators are in a purely combinatorial fashion. Okay, so let's let S, so maybe let's let H be the diagram. So it's the data of all of the sigma alpha beta z. Okay, so S of H is going to be the following set. It's going to be the set of tuples, G tuples of points, such that you have 1 point on each alpha and 1 point on each beta circle. Okay, so xi, we'll say, is in the intersection of alpha I intersect beta, some permutation so some element of the symmetric group. Okay, so now these are going to be eventually are going to be the generators of some kind of chain complex. Okay, now how many? So so these points will, in some suitable sense, will generate complex. Okay. Now, before I even tell you what that chain complex is, let's just think about a little bit of sort of elementary topology here. If I want to get a presentation for, let's say, either pi1 or h1 of the 3 manifolds, okay? So so as I said, we oriented the surface. I also want to treat all of the alpha and beta curves as having some orientation. And ultimately, things aren't going to really depend on that, but I want to have those things be oriented, okay? And let's let, I don't know, eta of x be the local intersection number. So for, maybe let's say it this way. For x in alpha I intersects beta j, let's let eta x be the intersection number. Okay, it's just going to be plus or minus 1. So now, how do we read off a group presentation for pi1? Well, what we're going to do is, if I want to think about my 3 manifolds, okay, I can think about it. I started with a 0 handle, okay? Then I attached some 1 handles, okay? And then I attached, and the the belt circles of the 1 handles were my alpha curves, right? And then I attached some 2 handles. And so if I want to read off a presentation for pi1, what do I have to do? I need to know when, as I trace around the boundary of the 2 handle, how does it run over the 1 handles? Okay. So what we'll do is, the group presentation pi1 of y is going to be generated by, let's say, a1 through ag, and then the words that we read off are going to be given by So the word is going to be, so take a beta curve, read around that beta curve, okay, and record how many, so this is going to be record intersections of beta j with alpha I, and those are going to be recorded as a word in these letters, so as a word in AI plus or minus 1. So the AIs and their inverses, okay, depending on the signs of intersections. And it's not too difficult to prove. It's going to be a nice little exercise. If you want to know, that's actually going to determine pi1 of the 3 manifold. Okay, and now of course, if we abelianize that, okay, then you get a presentation for pi1. Okay, so you can think about that as giving you a nice little presentation matrix. So if we abelianize, okay, let's write down the matrix M of H, let's say, which is going to be, it's going to be just the net intersection number of alpha I intersects beta j in the ijth entry, right? And that's going to be a presentation matrix. Okay? So what we conclude is that the determinant of M of H is, of course, is going to be equal to, or the absolute value of the determinant of M of H is going to be the order of H1 of y if this is a finite, and 0 otherwise. Okay? And this quantity I would like to define, so we're going to, I want to call that the determinant of the 3 manifold, just by analogy there. Okay? Now, what do these tuples of intersections have to do with anything here? Here's a nice little way that you might think about these things. I can write down a sort of another matrix here, which is going to be, let's consider the matrix whose entries are sort of formal linear combinations of the intersection points, such that so maybe, I don't know what to call this. Maybe let's call it M tilde of H is going to be the ijth entry is going to be the formal sum over x in alpha I intersects beta j of -1 to the eta of x times x. Okay, so I just want to think about that as sort of a formal linear combination of points. Okay. Then what can I do? I can take a determinant of that matrix, right? And that determinant is then going to be, so the determinant of M tilde. So now what am I going to get? I'm sort of going to get monomials, a whole bunch of monomials where the entries are going to be just sort of one point taken from each intersection, from each alpha and beta, and those are precisely, so this is going to be a formal sum of all elements of this set of intersection points, right? Because that's how if you've taught linear algebra, you've got to teach your students that there are signs involved in a determinant. Okay, so these are all going to come with some plus or minus ones, and the plus or minus ones are going to come from two sources. One is this local sign of intersection, okay, and the other thing that you get is going to be the signs that get built into the determinant. Okay, and of course, if you've taught linear algebra, you know that your students are probably pretty bad at keeping track of those signs. Okay, but that's actually going to be important momentarily. So, okay, are there any questions about any of this? This is probably all familiar, but I did want to express this perspective. Okay, so now let's start talking about. So that's the Heegaard side. Maybe we should now get a little bit into the Floer side. So what am I going to do? So what I would like to do is end up with a chain complex whose generators are precisely these objects. So I want to consider the symmetric product sim G of sigma, which is going to be the product of G copies of sigma modded out by the action of the symmetric group. Okay, so symmetric group on G letters acts on by permutations on this thing. Okay, now remarkably, this turns out to be a manifold. Okay, the reason it's a manifold, well, if you want to do this as this is a nice little exercise to work on, is so first understand why the symmetric product of G copies of the complex plane is a smooth manifold, right? Because of course this is not a free action, right? This action has fixed points, right? So you have to you're going to need a bit of work here. But the point is that if you the reason that the symmetric product of the complex plane is going to be a manifold can be summed up in 4 words as the fundamental theorem of algebra. So let's give this as a nice little exercise. This is a smooth 2G dimensional manifold. And in fact, if I make my sigma into a Riemann surface, then this becomes a complex manifold. Okay, the complex structure of the Riemann surface naturally translates into a complex structure on the symmetric product. Okay, now sitting inside of this this set is a space that I'm going to call T alpha, which is going to be the product of the G alpha circles. Okay, and that's just going to be a G-dimensional torus. Because if I take that G-dimensional torus sitting in here, then the fact that the alpha curves are pairwise disjoint means that they're going to project down when I look at the projection after I mod out by this action. That's going to remain an embedded G-dimensional torus. And similarly, T beta, which is going to be the product, also living in there. And now I have these 2 G-dimensional submanifolds of a 2G dimensional manifold. And how are they going to intersect? Well, T alpha intersect T beta is precisely going to be this set of intersection points that I described before, right? Because what is a point in that intersection? Well, it's a point that is being drawn from 1 point from each alpha circle, 1 point from each beta circle. That's precisely what we have there. Okay. Now, something that we should pay a little bit of attention to is the following. So, if x is equal to a tuple of x, x1 through xg in S of h, where xi is in alpha I intersect beta sub sigma of I. Here's a nice little fact that we should state. So now I have these two G-dimensional tori intersecting in a 2G-dimensional space, oriented G-dimensional space. I should talk about some kind of local sign of intersection. Okay, so the local intersection number of right. Well, so first of all, I guess one thing I should say is I can orient the curves, the 2 alpha and beta tori. Okay. Now, to orient them, I should just take the orientations on the alpha circles and take a product orientation. That's going to depend on the order of the components, the order that I've given here, right? If you swap the order, you change the orientation. Okay. So the local intersection number of T alpha and T beta at x, I claim, you can work this out, is going to be the product of the local orientation numbers, which I guess I called eta at xi, times the sign of the permutation. Okay. Now, Where has that number appeared before? It was in that determinant, right? So that, that determinant that I wrote down over here as a sort of formal linear combination, what were the if you work it all out, what are the signs that appear in front of any tuple here? It's precisely this intersection number, okay? Now, you may be wondering, why am I dwelling so much on that? And there's a good reason, we'll see. So up to an overall, so maybe I should call this quantity eta of x. Okay, so maybe I should just make this little observation that the sum over all x in S of h of eta of x, okay, is going to be equal to plus or minus the determinant of y, okay, right? Because just by construction. And now, of course, all of this depended on how I oriented things, okay? So how I oriented each of the curves and how I ordered each of the curves. So at least, so we're going to focus mostly on the situation where y is a rational homology sphere. So generally what we're going to do is we're going to choose the orientations that make this come out to be a positive number. Okay, very good. Why am I talking about so much about this? So now let's try to define a chain complex. Okay, and we'll do the most basic version here. Okay, so CF hat of the Heegaard diagram. Okay, I guess, so let's assume, I'm going to make some nice simplifying assumptions here. Assume we're talking about a rational homology sphere. Okay, so if y is a rational homology sphere, any Heegaard diagram will suffice for what I'm interested in. Okay? If not, if b1 of y is positive, we need to focus on a more restricted class of Heegaard diagrams that are called admissible. We can only work with admissible diagrams, and I'm not going to tell you what that means. You can look this up, but really the focus of many of the lectures in this both this series and some of the things that other people are going to be talking about is really going to be on the rational homology sphere setting. So I'm just going to bracket this. Okay, so, but assuming this diagram is admissible, then we can start writing down a chain complex. Okay, so now CF hat of the Heegaard diagram is going to be generated as an abelian group by all of these intersection points. Okay, and now it's going to come. So this complex, even before I tell you anything about a grading, about the differential, one thing I want to point out is that this has a natural Z mod 2 grading. Okay, which is just simply coming from given by this local intersection number. That's what the mod 2 grading is going to be. Okay, and now similarly, CF infinity of H is going to be generated over by the same set except now the generators are going to be given by elements of, or the base ring is going to be Z join UU inverse. Okay, so we can take sort of generators plus formal linear multiples. Now, sitting inside here is going to be what we call CF minus, which is going to be the generators that have positive U power. So okay, that's going to be the ones with strictly positive powers of U. Okay, and then the quotient CF plus of H is going to be defined as CF infinity mod CF minus. Okay, now of course I haven't told you what the differential is yet. So now we need some okay. So what's the differential? Right? I've like packed all of the. I've said all of the easy stuff now, and now I'm just going to introduce this. So that's all the Heegaard side. So let's get into the Floer side. Okay. So what I want to do is look at those two G-dimensional tori sitting in this symmetric product. Okay. So for now, suppose I have 2 points, and I really want to think about this now as the intersection of T alpha and T beta. Okay, so what can I do? I want to look at the, I can look at the path. Let's consider a path. A path that goes from X to Y along T alpha, and then back from Y to X along T beta. Okay? Now I can think about that as being an element of, I guess, pi 1 of the symmetric product. Okay? And I guess for, it's going to take some work, I guess, but for G greater than 1, pi 1 of sim G sigma it can actually be identified with H upper 1 of the 3 manifold. H, now I'm going to mess this up. Low. Oh, it's H1 of sigma. Right, there we go. Okay. So there's that loop. Okay, now, if that loop represents a trivial class, then what can I do? I want to think about disks. So I want to let, so we're going to consider disks, maps of a disk from, or maps from D2 into sim G sigma, okay, which are going to, whose boundaries are going to map to this kind of loop. Okay, so how do I want to think about that? I want to, so if I'm going to think, I want to think about the disk as sort of living in, we can think about it as living in the complex plane if we want. Okay, and we can let this be the point I, and this should be the point minus I. And I want to say that this point maps to X. This point should map to Y. And then the left-hand side should map to alpha, to T alpha. Oop. And the right-hand side should map to T beta. So such maps might not exist. Whether such maps exist is going to be determined by what path in pi 1 is represented by these generators. Okay, but assuming that that such a path exists, so what we want to do, so now what I'm going to denote by pi 2 of x comma y is going to be the set of homotopy classes of such maps. Okay? That set might be empty and it might be non-empty. And what we're going to be interested in is going to be holomorphic such maps. So I guess I need to say a little bit more. So the first question is going to be, how do I decide whether there are such maps? Okay, so here's what we'll do. So epsilon of xy is going to be, I can consider this kind of, it's going to be the following. So consider, if I want to consider, okay, so what is a path, first of all? A path in the symmetric group, or in a path in the symmetric product corresponds to a bunch of paths downstairs in the surface, right? Because any point in the surface is just a g. Any point on in the symmetric product is just a g tuple of points. Okay, so so epsilon of xy is going to be the following. Let's take arcs from like xi to yi along the alpha circles, and then from y sub I to x sub like j along the beta circles. Okay, so that's going to be so this is going to be a one cycle on sigma, okay, which is defined up to, now there are lots of choices here, right? I could take those paths up to multiples of the alpha and beta circles. Okay, so this is going to give a well-defined element of h1 of sigma mod the span of the alphas and the beta circles. But of course that is just h1 of y. Okay? And so my claim, and this is something you can check, is that pi 2, and this, all right, so epsilon of xy is going to be defined as this homology class here. Okay? So pi 2 of xy is going to be empty if epsilon of xy is non-zero, right? This is the obstruction, right? Precisely that. So that is going to be precisely the non-triviality of this path is going to be given by this obstruction. Okay, and if epsilon of xy is equal to 0, then this group is going to be given by so we'll say a little bit more about what this set is coming from. But so this epsilon class is going to be the obstruction to extending things. Okay, said a lot of things here. One more bit of background, which is going to be the following. What's this base point doing, right? Remember I said once at some point that we wanted to have a base point. But so for any point z in sigma that's not on the alpha or beta circles, okay, let's let v sub z be the subvariety of sim g of sigma, which is defined by forcing one of your g points, at least one of your g coordinates, to be equal to that z, right? So that's going to be a codimension 2 subvariety, right? I've imposed the codimension 2 condition of fixing one point, okay? So this is a sort of g minus 2, 2g minus 2 dimensional subspace. Okay, and what I can always do is intersect. So if I have a homotopy class of disks, okay, I can, there's a well-defined intersection number here, okay, because, well, this is a map of a disk whose boundary is on the alpha and beta circles, okay, and of course that must be disjoint from here because this point Z was disjoint from the alpha and beta circles. Okay, so that means there's a well-defined intersection number. Okay, and this depends only. So I'm going to call this NZ of phi. So this depends only on the number on the component of sigma minus alpha intersects beta containing Z. That is to say, if I move Z around, then I don't change this number, right? If I move Z around without crossing an alpha or beta circle, I don't change this number. Okay, so that is to say that so the domain of phi so that is going to be a what I'm going to mean by this is a formal linear combination of the regions of this Heegaard diagram. And by regions, I mean, look, the components of the complement. Okay, so this is going to be formal linear combination of the regions. Okay. And what are the coefficients? Well, the coefficients are going to be given in each place by these local multiplicities. Okay, and what I can say is this is, if you want to make this a little bit more concrete, it's a two-chain with boundary equal to that one chain, right? There's a one cycle specified by the 2 points, and the presence of domains of disks is going to be directly connected to the epsilons of to the whether or not you can find Whitney disks or these kinds of disks that are interpolating between 2 points is precisely the statement of whether or not I can find this chain epsilon is 0 in homology. Okay, so I've said a lot. I still haven't told you anything about the differential. And it turns out that actually this domain uniquely is how we specify the disk. So pi2 of xy is in one-to-one correspondence with such domains. Okay, so once I specify, so finding the disks, finding the domain, the homotopy class of disks is equivalent to this just linear algebra problem of finding all of the finding the domains in the surface that have these appropriate boundary conditions. Okay, maybe I'll leave that up there. Okay.
We have a standing assumption of genus bigger than 1, right? On the Heegaard diagram.
Yes. Well,
I mean, so
certain statements are a little bit different if I do the genus.
Calculation shouldn't have the z factor. In genus 1, the pi2 calculation shouldn't have.
That's right. That's correct. So yes. So genus 1 is actually much more. It's much easier to see what disks are supposed to be. They're just supposed to be disks. That was like the most tautological sentence I've ever said. Right. So in genus 1, actually, well, we're going to draw some pictures soon. So we'll get there. Okay. So now, so given x and y in phi in pi 2 of xy, I'm going to consider the moduli space of phi. Okay, well, so what do I have to specify? So first I specified a complex structure on the Heegaard surface. Okay, and when I specified the complex structure on the Heegaard surface, that translates into a complex structure on the symmetric product. And then for various reasons that are more complicated than I want to get into, you have to perturb that into an almost complex structure on the symmetric product. And that's going to be needed in order to achieve some kind of transversality. But once I've done all of that, okay, so this is going to be the moduli space of maps U from D2 into sim G sigma with the property, which are, U contained in this homotopy class. So that is to say, it maps I to X minus I to Y. The left hand arc goes to alpha. The right hand arc goes to beta. Okay, with the property that U is holomorphic. Okay, so that's obviously a very big constraint. And my claim is that this moduli space is under suitably generic conditions generically. So if the complex structures are chosen, or the almost complex structures are chosen suitably generically, M of phi is a manifold of dimension mu of phi, which is called the Maslov index. Okay, and the Maslov index can actually be given a very nice interpretation combinatorially, which, for lack of time, I'm not going to say because I only have 5 minutes to go. But this becomes a manifold. Okay, and now we can finally start giving some actual definitions. Oh, and it comes equipped with an R action, equipped with an action of R. What's that action? Well, I can identify the unit disk holomorphically with the unit strip. So maps of the unit disk, which are prescribed on I and minus I, can be identified with maps of the unit strip, which is to say, a vertical strip in the plane sending, plus infinity to one point and minus infinity to the other, plus infinity to x, minus infinity to y. Now, of course, I can reparameterize those things by vertical translation. Okay, this is the Riemann mapping theorem will tell you that you can do all of this. Okay, and that means that there's this R action. Okay, so now I can finally write down the differential. Okay, so the differential. So let's just focus on the hat case. Okay, we're going to define the differential of x to be equal to the sum over all y's. And now I'm going to sum over all homotopy classes of Whitney disks in between them, which have the property that their Maslov indices are equal to 1. So I'm only going to look at those particular ones. And I'm also going to require that the multiplicity at the base points is equal to 0. Okay? And so if this Maslov index is 1, then the moduli space is a one-dimensional manifold. And I can mod out by that R action, and now suddenly, oh, these turn out to be, these are compact, so I have suddenly a compact oriented zero-dimensional manifold. That's just a bunch of points. Okay, so I can count them. And this is going to be the differential that I write down. Okay, I've obviously squashed a huge amount of mathematics into saying this. Okay, and a miracle occurs, and theorem of Oshibas and Szabo is that d squared is equal to 0. Okay, so this is actually a legitimate differential, and the homology of this chain complex is independent of all sorts of choices. Okay, so what choices did I make? Number one, I chose a specific Heegaard diagram for the three manifolds. There are ways of trying to understand all of the different Heegaard diagrams that you could have for a given three manifold. Okay, and this is independent of that. I also made a choice of complex structure and almost complex structure. Okay, all of the analytic data that went into here. And the miracle that occurs is that this is actually independent. Okay, and this is what we call HF hat of the three manifold. Okay, as an abelian group. Okay, so maybe maybe before I get into more about this. I'm going to say a lot more tomorrow, but let me just make one basic observation here. Okay. Well, two observations. Okay, so number one, a little tight on time. So I had this function epsilon, right? This partitioning, this function epsilon on the pairs of generators. Okay. Now what that does is that partitions the generators into classes which are in one-to-one correspondence, as we said, with H1 of Y. Okay, so that is to say I get a decomposition of the three manifold. So if I have generators that are in different classes, then necessarily there are no disks connecting them. Right? That was what we said before. Okay, so what we end up with is that CF hat, and any of the versions, well, I didn't define the fancier versions of Y, splits as a direct sum of subcomplexes corresponding to those equivalence classes. And it turns out that there's a very natural way of identifying those equivalence classes with the spin C structures on the three manifold. And as a result, I get a direct sum. So there's my direct sum decomposition. Okay, right? Because these things are in one. H lower 1 of Y is the same as H upper 2 of Y. Boundary equality. Okay, that's the one statement. Now let me just say one final thing about where this group is showing up here. Okay, so it turns out, assuming if Y is a rational homology sphere, okay, then this group can actually be given a relative Z grading, or each well, I guess the whole. So actually, I guess I don't even need to say anything about the relative Z grading. I have a Z mod 2 grading. Okay, so CF hat has a Z mod 2 grading. Okay, what is it? It's just the as I said before, it's given by the local intersection numbers. And it turns out that the differential shifts the Z mod 2 grading by 1. Okay, so D shifts grading by 1. And so what do we see? We see that the Euler characteristic of CF hat of y is equal to the Euler characteristic with respect to, CF hat of y. The Euler characteristic of CF hat of y is equal to the weighted sum of generators, right? But we said what that is. That was equal to the determinant of y. Okay? And of course, that's equal to the Euler characteristic of the homology, right? Because Euler characteristic doesn't change when you take homology. Okay? So now, what's the very last thing we can say? If I have a homology group, the rank of the homology is always at least as big as the Euler characteristic. Okay? So there's an automatic lower bound that I get on the rank of the Heegaard Floer homology of a three-manifold. Okay? So one very natural question one can ask is, what are the three manifolds for which that bound is the equality, for which the Heegaard Floer homology is sort of as small as it can be? And those are going to be the L spaces that are going to be talked about a lot throughout the course of this week. So I'll pick that up more tomorrow. So I'll stop there.
So we now have 25 minutes to drink coffee. Thanks, Adam.